In the vast expanse of our universe, where the night sky is adorned with countless stars, there lies a story that begins not with light, but with darkness. A story of creation, of chaos, and ultimately, of order. Imagine, if you will, a time before planets existed. A time when the cosmos was a swirling cloud of gas and dust. A primordial soup of materials waiting to coalesce into something magnificent. This is the tale of planetary formation and evolution, a journey from tiny dust particles to fully formed planets. Let's start at the very beginning, shall we? Picture the early solar system, around 4.6 billion years ago. It was a chaotic place, a swirling disk of gas and dust orbiting a young star, our sun. This disk was made up of remnants from the formation of the sun itself, along with heavier elements that had been forged in the hearts of ancient stars that exploded in supernovae. These elements, hydrogen, helium, carbon, oxygen, and a plethora of others, were like the building blocks of a cosmic Lego set, just waiting to snap together. Now, in this disk, gravity was the unsung hero. It began to pull these tiny dust particles together. At first, they were just that, tiny particles, almost like grains of sand. But as they collided and stuck together, they formed larger clumps, known as planetesimals. Think of these planetesimals as the first seeds of a planet, each one a potential world. Some were small, others quite large, but they all shared a common destiny: to grow. As these planetesimals collided, they began to merge, and over millions of years, they formed protoplanets. This was a time of intense activity, with bodies crashing into one another, creating craters and debris, and releasing energy that heated their surfaces. Imagine the violence of these collisions, akin to cosmic bumper cars, but on a scale we can hardly fathom. The heat generated from these impacts, along with the gravitational compression, caused the interiors of these growing protoplanets to melt, leading to differentiation. The process where heavier materials sank to the center, while lighter materials floated to the surface. This differentiation is crucial because it laid the groundwork for the layered structure we see in planets today. The densest materials, like iron and nickel, formed the core, while lighter silicates created the mantle and crust. Earth, for instance, has a solid inner core, a liquid outer core, a viscous mantle, and a rocky crust. Other planets, too, followed this blueprint, but each one took on its own unique characteristics based on its distance from the sun, its size, and the materials available to it. But wait, let's not forget about the role of the gas giants. While the inner planets, Mercury, Venus, Earth, and Mars, were busy forming from rocky materials, the outer planets, Jupiter, Saturn, Uranus, and Neptune, had a different fate. These behemoths were able to capture and hold on to vast amounts of gas due to their massive sizes and strong gravitational pulls. They formed from the same process of accretion, but their ability to gather hydrogen and helium from the surrounding disk allowed them to grow into the giants we see today. As these planets continued to evolve, they experienced their own unique journeys. Some, like Earth, became hospitable to life, while others, like Mars, lost their atmospheres and became barren wastelands. The differences we see are largely due to their positions in the solar system and the conditions they faced during their formation. For instance, Earth's distance from the Sun placed it in the so-called Goldilocks zone, not too hot, not too cold, allowing for the presence of liquid water, a critical ingredient for life as we know it. Now, let's talk about moons, because they have their own fascinating stories. Many moons formed from the debris left over after the formation of their parent planets. For example, our moon is thought to have formed from the debris created when a Mars-sized body collided with the early Earth. This event was catastrophic, but it also set the stage for the moon's formation, which would go on to influence Earth's tides and stabilize its axial tilt, creating a more stable climate. And then there are the icy bodies found in the outer solar system, like comets and asteroids. These remnants from the early solar system tell us a lot about the conditions that existed during the formation of the planets. They are like time capsules, preserving the chemical signatures of the early solar system. When we study these objects, we gain insights into the building blocks of planets and the processes that shaped them. Some scientists even speculate that comets may have delivered water and organic materials to Earth, contributing to the emergence of life. As we zoom out and take in the big picture, it becomes clear that the formation of planets is a complex interplay of forces: gravity, heat, and the fundamental laws of physics. It's a dance that has been ongoing for billions of years, leading to the diverse array of worlds we see today. From the scorching surface of Venus to the icy rings of Saturn, each planet is a testament to the dynamic processes that govern our universe. But the story doesn't end there. Planets are not static. They continue to evolve over time. Geological activity, atmospheric changes, and even the influence of other celestial bodies can reshape a planet's surface and environment. Earth, for instance, is a dynamic world, constantly changing due to tectonic activity, erosion, and climate shifts. The same can be said for other planets, albeit in different ways. Mars, once a vibrant world with flowing water, is now a cold desert, while Jupiter's Great Red Spot, a massive storm larger than Earth, has been raging for centuries. As we explore our solar system and beyond, we are beginning to understand that planetary formation is not a unique event limited to our own neighborhood. The universe is filled with exoplanets, planets orbiting stars beyond our solar system. With advances in technology, we have detected thousands of these distant worlds, each one offering a glimpse into the processes that govern planetary formation on a cosmic scale. Some of these exoplanets are strikingly similar to Earth, located in their own Goldilocks zones, while others are gas giants or icy worlds that challenge our understanding of how planets can form. The diversity of these planets suggests that the processes of planetary formation are not only fascinating, but also incredibly varied. Each star system has its own unique history and conditions that shape the planets within it. Now let's take a moment to reflect on what all of this means for us as inhabitants of Earth. Understanding planetary formation and evolution is not just an academic exercise. It has profound implications for our place in the universe. It raises questions about the potential for life elsewhere, the future of our own planet, and the fate of our solar system. As we continue to explore the cosmos, we are reminded of our own origins and the delicate balance that sustains life on Earth. So, as we look up at the night sky, let's remember that we are part of a grand narrative, a story that stretches back billions of years, from the tiniest dust particles to the majestic planets that orbit our sun. Each star we see is a potential cradle for new worlds, and each planet tells a story of its own. The universe is a tapestry woven from the threads of time, and we are but a small part of this incredible journey. In conclusion, the formation and evolution of planets is a testament to the power of nature and the laws of physics. It is a reminder of the beauty and complexity of our universe, and it invites us to continue exploring, questioning, and marveling at the wonders that surround us. As we venture into the unknown, let's carry with us the knowledge that we are part of something much larger, a cosmic story that is still being written, one dust particle at a time.